So now we're going to be talking about the column space of A. We're going to be denoting that CS. And when I say column space, it's pretty obvious what should come to your mind. Probably columns, right? Yeah, so our column space of A is going to be the span of the columns of A. So we're just going to pull out our columns of A. So we are defining our column space of A as the span of the columns of A. Kind of the name goes right into it. So now we are looking at all linear combinations of the column vectors of A. So we already have a set defined. We don't have to try and find it, like search for it like we had to do with the null space. So we have it defined, but we want to find a basis for our column space. So if you remember, we need our basis to first span the whole set. So we already know that this spans it, but we also need it to be linearly independent. So let's see how we can define our basis of our column space. So what we're going to do is we're going to take the columns of A and we're going to put it into row echelon form and see if they are linearly independent. So once again, we're going to be augmenting it with the zero matrix to see if it is linearly independent. Okay, so we're going to be doing the exact same row operations we did to find our null space. So let's just get those out of the way. So once we have row reduced our matrix down to reduced row echelon form, we are left once again with this matrix. So we're trying to find the basis for our column space. So what we're going to do is we're going to take our columns with pivot variables right here, and these are going to be the basis for our column space. However, it's not these specific columns, but instead that means we're going to go back and like, okay, so our first and our third columns, so we're going to go back and find our first and third columns, and these are going to be the basis of our column space. So our column space of A is still going to be the span, but it's going to be the span of just these two vectors. So you'll notice that we can actually write these two columns as linear combinations of these two columns. Column 2 is just a scalar multiple of column 1, and column 4 is a little bit trickier than just, it's just a regular multiple of one of the other columns. But we'll see that this here now is our linearly independent set, and it spans all of the columns. So it's not only going to give us these two vectors, but it's also going to give us all linear combinations of these 4 vectors, because we can create each of these vectors from a linear combination of these to start with. So our column space here is going to have a dimension of 2. So that refers to the 2 columns here that we have with a pivot variable in it. So you'll find that our column space is going to have, the basis of our column space is going to have the same dimension as the number of columns with a pivot variable, or the rank of our equation. So now you'll think, okay, so the relationship between our column space and our null space, if we have our null space is just equal to the 0 vector, that means that all of the columns are already linearly independent. So that means that our column space is just going to be the span of all the vectors, and we don't have to try and find a new basis. So why do we care about this column space? We know that it has dimension 2. We know that it spans all of our columns, and that means that we have all linear combinations of our columns. But like, why do we need it? It actually really helps us when we're solving equations such as like A times x vector equals our b vector. We know that we have a solution if our b vector is in the span of our columns. So if our b vector is in the column space, that means that we have a solution. If it's not, then don't even bother trying to find it. So now that we've learned a little bit about column space and null space, We have some really cool properties, how they intertwine, and those are super fun to explore. So go have fun, enjoy the null space and column space, and we'll see you next time.